So we see in the last video that the Earth's atmosphere is broken up into these different areas according to height above the ground, but also what happens to the temperature. Okay. All right. So let's just move on to the next one. All right. So the next we're learning about the fact that, of course, that we get radiation from the sun. That's our primary source of heat. And it's in the form of electromagnetic radiation, which, by the way, allows it to cross the vacuum of space. And most of the electromagnetic radiation, there's lots of different forms of it. Most of it comes to us in the visible form, right? From 400 nanometers to 700 nanometers, and also other types of radiation, radio waves, microwaves, things like that as well. And of course, our atmosphere blocks most of the ultraviolet radiation. Right. So when the radiation hits our planet, hits the land and the water, what happens is that the visible, which is remember, this is primarily what the solar radiation is composed of, is this visible wavelengths. And there's no accident that our eyes are sensitive to these particular wavelengths. But anyhow, what happens is when that radiation gets absorbed, it gets turned into a longer wavelength. Longer waves, of course, are less energy, and so some of the energy gets absorbed by the earth, by the water, by the actual ground, but then the other is re-radiated back, and in all directions as it's called terrestrial radiation. All right, it's just the re-radiated visible radiation. It's just called terrestrial radiation because it comes from the Earth. But remember, it originally got here from the sun, and it's of course a longer wavelength. Therefore, it's in the infrared. All right, so that's the main part. There's right here. It's in the infrared wavelengths. All right, so now there are certain gases in the atmosphere that will trap the infrared. Will prevent it from escaping out into space. And those gases, of course, are water vapor and carbon dioxide. There's actually other ones. There's nitrous oxide, and to a much less extent, and CFCs, chlorofluorocarbons, and other things like that. But anyhow, the ones that are natural that we find in the atmosphere, of course, are water vapor and carbon dioxide. Right, so the sun warms the earth, the ground turns that heat energy back into this thing called terrestrial radiation, and really that's what causes the atmosphere to be warmed up is this terrestrial radiation coming from the ground. Right. Okay, so let's see. So the Earth's temperature varies according to the degree of solar intensity. So you kind of think that there should be a good picture of this for us to understand this. Here, let's. So it's really the amount of radiation per area. Where the intensity is higher, the temperature is higher. Here, so this is a perfect picture. Okay, this is exactly what I was looking for. All right, so you have a flashlight. It's putting out so many watts of power, and if the flashlight is as it's shown right here, shown straight down where the beams of light are more or less perpendicular to this piece of paper, then this is the most intense that the light is going to be, right? So the area is as small as it can possibly be. Whereas if you tilt the flashlight, it's the same amount of power. It's the same energy per unit time that's coming out of the flashlight. But because you're at some angle, the area is greater. And the fact that the area is greater means that the intensity, when you compare it to the intensity up here of the light, the intensity is less. The energy per area is smaller because you have a greater area, right? That's the basic idea. So this is a weaker intensity. This is the strongest intensity, and of course the more the greater the angle. If I bent this flashlight down, that would be even less intensity, right? And this really has to do with the latitudes. Like if you think about our Earth, the sunlight is coming down. This would be right at the equator, and then as you get closer and closer to the North or the South Pole, the rays of light are spread out over more area, and so being less intense. So the North and South Poles are much colder than at the equator, right, where the energy is more intense. All right, so now. So that's just something that normally happens every single day, but of course, as our Earth as this picture shows, our Earth goes around the sun, and the Earth is tilted. It's tilted by about 23.5 degrees, and that tilt stays the same. Okay, so as it goes around the sun, it is always tilted in the same direction. And that's, for example, the reason why if you're in the northern hemisphere and you know where the North Star is, that is always in the direction of the North Pole. All right, so you look up in the night sky, and if you can see what's called the North Star, also known as Polaris. If you can find Polaris, you always know the direction of north. All right, so here's what happens. All right. So we go back to this flashlight thing. This is showing the different intensities. Well, that's fine, and that happens, of course, with respect to the you get the most intense light at the equators, the least intense at the poles. But see, here's the thing: as the Earth goes around the sun in the course of a year. There are times that the northern hemisphere. So here, let me start up over here on this side, on the left hand side. So there are times when the northern hemisphere is tilted towards the sun, and that of course is the first day of what we call the summer solstice, right? So the summer solstice is when the tilt of the Earth is as much as it's ever going to be. So the northern hemisphere is tilted as much as it's ever going to be towards the sun. So the northern hemisphere is tilted towards the sun, and the southern hemisphere is tilted away. So the beams of light that are coming from the sun are more concentrated. They're more intense in the northern hemisphere on the first day of the summer solstice, which in the calendar year, that happens usually on June 21st, roughly June 21st. It's not always exactly the same day because, the year is not exactly 365 days. All right. So anyhow, so you go, so as time goes on, so what's going on here? Areas in the north of the equator, these on this day, they have the most sunlight in a 24-hour period, and the least amount of nighttime, right? All right, so the Earth is moving around the sun. It takes to go from the summer solstice to what's called the autumnal equinox. Well, actually, here we'll skip that for right now. So 6 months later, the sun is on the other. The Earth is on the other side, and remember the tilt has not changed, so that now the southern hemisphere is tilted towards the sun, and the northern hemisphere is tilted away from the sun. And you can see that in this picture, right? So the northern hemisphere tilted away, and so the sunlight is less intense for the northern hemisphere, but more intense for the southern hemisphere. And so that's the first day of winter. It's usually around December 21st or so. Again, it's not exactly the same day each year, because of course it's not exactly 365 days in a year, in a calendar year. And so what's happening on that day, that's actually the first day of summer if you live in the southern hemisphere. Of course, there's a lot less land in the southern hemisphere, but people in Australia, in South Africa, in most parts of Brazil and South America, that's the first day of summer. But in the calendar year, that's December 21st. And of course, for people in the northern hemisphere, that's the first day of winter. All right, so let's continue. So from the first day of winter, again, the sun is still I should go over this real quick. So the people in the northern hemisphere get the least amount of daylight, and they get the most amount of night. And then it's opposite in the southern hemisphere, right? They get the most amount of daylight and the least amount of nighttime, for a single day, right? And so then gradually it changes as the Earth moves into it moves over to what's called the vernal equinox, which is of course the spring equinox that happens usually around March 21st. And so so what's going on here, of course, is it's been 3 months since the winter solstice in the northern hemisphere, and so when the Earth is in this position, this is what's called the equinox. So there's an equal amount of day and night, and this is true all over the globe, all over the world. And so that's the first day of it. It's the first day of spring in the northern hemisphere, because after that you're heading towards summer. The first day of summer in the northern hemisphere, it's 3 months later, and then 3 months after that, which we skipped initially, 3 months after the summer solstice, we're back to half, equal amount of day and nighttime, and that's called the autumnal equinox, or the fall, the first day of fall. In the northern hemisphere, it's the first day of fall. In the southern hemisphere, that would be the first day of spring, right? Because it's you're heading towards summer in the southern hemisphere, right? Which would happen December 21st, right? And it just keeps repeating over and over, right? And so that's varying the amount of intensity over the course of a year. So the sun's rays are closest to perpendicular on any spot in the world when it's summer. That it's most intense. 6 months later, it would be the winter time. You have the greatest angle, and of course, in between, you get the fall and the spring. Right. So and of course, they're completely they're opposite in the southern hemisphere. People forget that a lot. They think that December 21st, it's automatically winter. And it is for the northern hemisphere, but the people in the southern hemisphere, which there are, lots and lots of people in the southern hemisphere, that's their first day of summer. All right, yeah. So here, let's go to the next one. Now, of course, this is I'll cover more of this. I'm about to lose the thing. I'll cover this in the next video, but. What's happened is the amount of carbon dioxide has risen dramatically